Hey, in this tutorial we're looking at general solutions of trigonometric equations. So I've got a summary here of our results that we get. So in this we need to really be using our unit circle and some of our exact values. So I've got where our two solutions lie for sine. We have one here in the first quadrant, okay, and then we have one in the second quadrant, remembering that our solutions in the second quadrant are pi minus theta. Okay, and we call this theta here our basic angle. Okay, so we're basically saying if sine of x equals a, then we have two solutions. We have one here, okay, which is given by 2 pi n plus the inverse sine of a. So that's basically saying our basic angle here, if we take the inverse sine, our basic angle in the first quadrant, okay, and then we get this same solution again whenever we add multiples of 2 pi to our solution. Because if we're here, okay, and we add on 2 pi, then we're going to come around and back to the same answer. Okay, and it all comes back to that cyclic nature of our trig graphs. So if you like to think of it graphically, okay, if we draw a little sine graph here, okay, and it's some value here that we're solving our equation for, you can see, well, we get a solution here, and we get a solution here, and we get this same solution, this first one, when we've added 2 pi to it. And same here, this is this solution with 2 pi added to it. Okay, and so n could be 2, and that would mean then that we're going to add 4 pi and we'll get our next solutions here. Okay, so that's for this angle here. Okay, now for this angle here, okay, it's a little bit different. Okay, we've got to say that we've got 2n plus 1 times by pi, take away the inverse sine of a. Okay, so the idea here is that we want odd multiples of pi and that are increasing by 2 pi. So for example, if we said that n was 0, well 2n would be 0 plus 1, so we'd just be saying 1 times pi is pi, take our inverse sine of a, which is taking this angle. Okay, so that would give us our first solution, okay, of pi minus theta. If we said, however, that n was 1, well, 2 times 1 is 2, plus 1 is 3, so now we're saying 3 pi. Take inverse sine of our angle. So that's just meaning that we're here and we're going around another 2 pi to get back to what we are. Okay, so our sine is actually our most complicated in this case because we've got to represent it as two different functions. If we have a look at cos, however, okay, it works out nicely for cos, okay, that we can say, well, if cos of x equals a, then x equals 2n pi plus or minus the inverse cos of a. And that's basically because we've got one solution here in the first quadrant, and our second solution here is in our fourth quadrant, which is found by going 2 pi minus theta. Okay, so basically every time that we add 2 pi to this one, okay, well that's where we're using our plus. We've got 2n pi plus our inverse cos, that's this one. We're going 2n pi minus the inverse cos, well that's this one. And again, it's just about cycling through our different results. And for tan, we have a solution in the first and third quadrants. Okay, and for that, it's simply n pi plus inverse tan of a. And so that can be plus or minus there. It doesn't, no, sorry, not plus or minus there. It can really be plus or minus over here. Okay. In the book, they just talk about plus because it doesn't matter too much. We keep cycling through. But if we were going to take away, well, we could come back this way and get this solution as well and keep coming back around that way, or we can go around this way and get our solutions. Okay, so we'll just worry about it where we're just saying that it's n pi plus inverse tan of theta, okay, just so it sticks with what we have in our textbook. Okay, so this is just basically because our answers for tan are separated by pi radians from each other, which is quite handy. So we'll have a look at a worked example for each of these different ones. Okay, and these are worked examples out of the textbook. Okay, so we're looking at find the general solution to the equation sine of x equals root 3. Root 3 on 2. Okay, so the first thing we need to do is go, well, what is our inverse sine of root 3 on 2, and that is, okay, what is our basic angle? Okay, now we could use our calculator for this. That should be inverse, sorry. Use our calculator for this, or using our exact values, and we find that it is pi on 3. Okay, so now we basically need to use our two solutions. So remember, our two solutions are x equals 2n pi, and we'll have plus pi on 3, or x equals 2n plus 1 pi minus our pi on 3. Okay, so if we just have a look at this one to start off with, okay, it's just a little bit of rearranging. By convention, what we do here, okay, is we actually take out pi on 3 as a common factor. Okay, and it seems a little bit odd, but it just makes our answer look a little bit nicer. So we take out pi on 3, okay, and what that leaves us with then is 6n plus 1 left inside our brackets. Okay, and you can multiply back through to double check, because if we multiply through with our pi on 3, will be 6 pi n divided by 3, which is the same as 2n pi. Okay, for our other solution, okay, what we need to do first is expand out our brackets. So you get 2n pi plus pi minus pi on 3. Okay, so we have 2n pi, and pi minus pi on 3 gives us 2 pi on 3. Okay, and again what we do is we take out 2 pi on 3 out as a common factor, okay, which will leave us with 2 pi on 3 outside of 3n plus 1. Okay, and there are our two solutions, here and here. Okay, and they're all our general solutions, so that they define all the possible solutions for this equation, because again we can just use values for n, and I should actually stipulate, I forgot about that, where n is an element of z. Now z is just our set of our integers, so it's all our whole numbers that we're talking about there. Okay, so we'll have a look at our second worked example. This one's a little bit nicer, okay, because again we need to be looking for what our basic angle is, or finding out what x equals. So really we need, well, what's the inverse cos of a half? Okay, and again we can use our calculator, or we should be using our exact value tables. Hopefully you should get pretty good at these and be able to know these off the top of your head. Okay, and again we actually have the angle pi on 3. Okay, so simply now we just need to say, well, x equals our 2n pi plus or minus pi on 3. Okay, and again, just as we did for our convention here, we're going to take out pi on 3 as a common factor. Okay, and it's going to leave us with pi on 3 outside of 6n plus or minus 1. Okay, just taking out that pi on 3 as a common factor from both our terms. Okay, so you can see less work because our two answers are given in the one equation because of our ability to do our plus or minus. Okay, so we'll look at the last little example that we've got here. Again, we need to work out what our basic angle is. Okay, so we go, well, what's the inverse tan of root 3? Okay, and again, textbook's not very creative here. Okay, we're using pi on 3 as our angle. So we simply use our rule, which is x equals n pi plus pi on 3. Okay, and we're going to take that out, our pi on 3 out as a common factor again. Make it 3n plus 1. Okay, where n is an element of z, and I forgot to do that here as well, where n is an element of z. Okay, you need to get used to doing that as well, because that's our full solution. Without our stipulation of what n is, then we haven't actually fully answered it. Okay, we'll look at another couple of examples. Okay, equations are reducible to quadratics. Okay, this is a really typical exam type questions. It's something that when you look at it to start off with, it looks quite complicated and you go, how am I ever going to be able to do this? But you'll be able to see that it actually works out to be solvable using quadratics. Because essentially, okay, think of our general quadratic formula. Okay, well, we have y equals ax squared plus bx plus c. Well, we've got something that's squared, and we've got that same thing again, and then a constant. If you have a look here, we have this sine of 2x that's being squared here. Okay, so we've got something times something squared, and then that same thing again, and just another constant. Okay, so what we need to do here, okay, and I'll just rewrite the question out so we can get a bit of working out going nicely. So you have 2 sine squared of 2x plus sine of 2x take 1 equals 0. So what we do here is we say let u equal sine of 2x. Okay? Therefore, what we have is 2 times u squared plus u take 1 equals 0. So you can see now that we actually have a nice quadratic. Now, you don't have to use u. Okay? The main thing is not to use is x if it's in the equation, or y if it's in the equation. Make sure you use some other variable. Use one that we use a fair bit. Okay, so what we're going to do now is we can factorise that, and you'll see that we'll get 2u take 1 times by u plus 1 equaling 0. Okay, and the beautiful thing about that now is, well, we'll go our null factor law. So our null factor law, okay, remember that means that if this is going to equal 0, then either that equals 0 or that equals 0. So means that 2u take 1 equals 0, or u plus 1 equals 0. Okay, what we need to do at this stage is sub u equals sine of 2x back in. Okay, so our first equation, I'm going to label it 1, I'm going to label it 2. So our first equation, okay, becomes 2 sine of 2x take 1 equals 0. And our second equation, okay, is going to be sine of 2x plus 1 equals 0. Okay, now in this case we do actually have solutions for both of these. Okay, but you need to be aware that sometimes when you do this, one answer will drop out. Like for example, if this was plus 2, then we'd be subtracting 2 away, and there's no way that we can have our sine function equaling negative 2. Okay, so in that case we could ignore that equation and just focus on the 1. However, in this one, we can actually further explore both of them. So we'll look at equation 1 to start off with. Okay, so we've got 2 sine of 2x minus 1 equals 0. We'll just rearrange that. Say, well, we've got sine of 2x equaling positive a half. Okay, at the moment. Okay, so that works out well. So now we can start looking at our 2 different solutions. So we need to go, okay, well, what is the inverse sine of a half? Okay, so what do we get? What angles can we use to get a half? Okay, and for that it is our pi on 6. This is a half. Okay, so now we can start setting up our equations. Okay, and say that, well, we've got 2x equals 2n pi plus pi on 6. Okay, we'll take out our pi on 6 as a common factor first. 2x equals pi on 6 outside of 12n plus 1. Okay, and now we can divide by 2. So we get x equals pi on 12 outside of 12n plus 1, where n is an element of z. Okay, so we could have divided by 2 back here, okay, but it just actually made it a little bit simpler to take out pi on 6 as a common factor first, because then we simply just have to multiply our denominator by 2. Okay, now we need to look at our other solution. Okay, so there's one solution there. Okay, which is when we've got 2x equaling 2n plus 1 outside of pi minus pi on 6. I'm just having pi on 6 straight in because we know it. Okay, so we need to expand our brackets first. We've got 2n pi plus pi minus pi on 6, okay, which is our 2n pi. That will be plus 5 pi on 6. Okay, we've got so far. So if we take out pi on 6 as a common factor, then we're going to be left with 12n plus 5. And you see I didn't take out 5 pi on 6, it's just pi on 6. It doesn't matter too much, it's as long as it's something that takes out the pi from both of them. Okay, and it makes it look simpler. Okay, we don't want to just take out pi and leave this as 5 on 6, because then we've still got a fraction in our bracket, so we want to get rid of that. Okay, now we simply divide by our 2, we get x equals pi on 12, side of 12n plus 5, again, where n is an element of z. Okay, so it was working with equation 1. However, we've got to work with equation 2 as well. Okay, so working with equation 2. Okay, this was our one here, which was sine of 2x plus 1 equals 0. So rearranging, we'd say that sine of 2x equals negative 1. So again, what's the inverse sine of negative 1? Okay, and we find that that is our answer of pi on 2. Okay, so what we need to do here is, sorry, it's actually negative pi on 2, not pi on 2, so my mistake. So now we're saying, well, we've got 2x, okay, equaling our 2n pi, take pi on 2. Okay, it's not plus this time, it's take. Okay, bit of rearranging. Again, we're going to take our pi on 2 out as a common factor. Okay, to give us pi on 2 outside of 4n, take 1. Okay, divide by our 2, we end up with pi on 4 outside of 4n, take 1, where n is an element of z. Okay, and we need our second one, okay, where we have our 2x equaling our 2n plus 1 pi plus pi on 2, okay, because of the double negative, okay, which means we're going to have to expand out our brackets, and we've got 2n pi plus pi on 2. Okay, so then we have 2n pi plus 3 pi on 2. Okay, we're going to this time bring out our pi on 2 again. So we've got pi on 2 outside of 4n plus 3. And we're going to divide by our 2 to get pi on 4 outside of 4n plus 3, where n is an element of z. Okay, so that's all our solutions. Okay, so we've got this one here, this one here, we've got one over here, and we've got one there. Okay, so we've got one last worked example to do, which is trig equations involving multiple angles. So find the general solution to cos of 4x equals sine of 2x. Okay, so obvious problem here is that we have cos and sine, okay, in the same equation. You could be tempted to use to try to divide or multiply something here to end up with tan because we've got sine and cos there, but the problem with that is we don't have the same angle in here. So what we're going to use is one of our identities that's sine of pi on 2 minus a equals cos of a. So we're going to do that because when we're working with that, then we can say, well, our equation here, we've got our cos of 4x, oops, equaling, well, we can say our sine of 2x really becomes cos of pi on 2 minus 2x. Okay, is what we can do there. Okay, and it just makes things work a little bit nicer for us. Okay, because now we can look at our equations. Okay, here. Okay, and say, well, we really say our 4x equals 2n pi plus or minus, okay, what's in our bracket here? Our pi on 2 minus 2x. Okay, is what we're going to do there. Okay, so we'll just look at the positive one to start off with. So we'll say, well, 4x equals 2 pi n plus pi on 2 take 2x. Okay, so we can simplify that a little bit because what we can do is we can bring this 2x across this side and say, well, we've got 6x equals 2 pi n plus pi on 2. Okay, and we take our pi on 2 out as a common factor and say, well, we've got 6x equals pi on 2 outside of 4n plus 1. Okay, and we can divide by our 6 to get x equals pi on 12 outside of 4n plus 1. Okay, and we just need to say, as always, where n is an element of z. And we can look at our other case where we're using the minus. So we're saying that we've got 4x equals 2n pi minus pi on 2 take 2x. Okay, I'm doing that deliberately because we need to make sure that we do our double negatives. Okay, to say that we've got 4x equals 2n pi minus pi on 2 plus 2x, which means we can take it away and leave us with 2x equaling 2n pi minus pi on 2. Okay, take our pi on 2 out as a common factor. Okay, we're going to get pi on 2 outside of 4n take 1, and we can divide by 2 to give us x equals pi on 4 outside of 4n take 1, okay, where n is an element of z. So we've got our two solutions. Okay, so there's a little bit to this section. Okay, hopefully it'll tie in fairly well with what we've done in our method studies as well, but hopefully that's enough to get you through this section.